So let's apply this idea of calculus to those travel graphs. Things we talked about before was displacement. Now, in maths we often use x, because a lot of our examples we say, oh, imagine a particle is just moving on a horizontal line, and horizontal line conveniently we can think of as the x-axis. So often we use the pronumeral x to represent displacement. In physics I think they often use the letter s. It doesn't really matter, it's just a pronumeral. So displacement, different from distance, because it has direction as well. So it's distance from a point, but with direction. So some point will be defined as the starting point. We can think of that as 0, unless they define it as something else. So if it was on the left-hand side, it would be negative, and on the right-hand side, it would be positive. Now, velocity is simply the change in displacement. That's what we said before. Change in displacement. So the symbol's logically v for velocity, but we could think of it as the first derivative of displacement with respect to time. So dx to t. How does displacement change over time? Another notation we use in calculus, but purely when we're dealing with motion, we don't tend to use it in other problems, is the dot notation. So x with one dot on top is another way of saying the first derivative of velocity. So it's the rate of change of displacement with respect to time. So it's speed, but with direction. So again, which way are we travelling? And then the third component to complete the whole picture of motion is acceleration. And acceleration is a rate of change as well. All acceleration is the rate of change of velocity with respect to time. And so A for acceleration, well, if it's the rate of change of velocity, we could use dv to t. We could use the second derivative of displacement with respect to time. And using the dot notation, I could use x with 2 dots to say it's the second derivative, or I could use v with 1 dot, so it's the first derivative of velocity. They're all notations that we could use. Now, acceleration is an unfortunate one because displacement I can say is distance with direction. And velocity I can say is speed with direction. But acceleration is acceleration with direction. It's the same word we use in both contexts, so it can sometimes confuse people. And some people use this word deceleration to mean that they're slowing down. There is no such thing as deceleration. Okay, it doesn't exist. It's just a word people have made up. What it basically is when your acceleration is in the opposite direction to your velocity. So, do you remember one of Newton's laws, force equals mass times acceleration? Okay. So acceleration, think of it like a component of force. So if you're travelling along, hey, I'm going to travel this way in the positive direction. Here I am, travelling in the positive direction, and someone pushes me in the back. They apply a force, but it's in the same direction that I'm travelling. What am I going to do? Fall over? Well, yeah, maybe fall over, but I'm going to speed up. They're going to push me. It's going to make me go faster. That's acceleration. But if that person instead was to grab my shirt and pull me backwards, I'll slow down. So when that force, that acceleration, is in the opposite direction to which I'm travelling, that's when we slow down. That's what people think of as deceleration. It's not deceleration, it is still acceleration, but in the opposite direction to which you're travelling. So if I'm travelling in the positive direction, my acceleration is in the negative direction, I'll slow down. It doesn't have to be in the positive direction. If I'm travelling in the negative direction, but acceleration is in the positive direction, I'll slow down. Opposite signs. I just keep putting this slide in because I like it. Watch this. Oh yeah, you'll love it. To get from displacement to velocity, you differentiate. And to get to velocity to acceleration, you differentiate. Which means if we want to go back the other way, we integrate. Yeah, okay. I just saw it in a newspaper years and years ago. I thought, oh, that's kind of cool. Anyway, let's have a look at our travel graph. The other thing that can now happen is we can have negative numbers, because I'm not talking about distance versus time, I'm talking about displacement versus time. So you'll notice there's negatives. It goes below the time axis as well. Now, at any particular point, see, average velocity is great, but it's not very useful. You usually want to know how fast am I going now. I want to know instantly, what am I doing? If you're in a car and the police pulls you over and says, sorry sir, this is a 60 zone, I believe you were going at 80 kilometres per hour. You can't turn to him and say, oh, but that's all right sir, I was stationary 5 minutes ago. So if we take my average velocity, I'm within the speed limit, okay? He'll give you a ticket pretty quick and probably start going over your car, look for defects and things like that. Okay, so instantaneous. Well, now that we know calculus, we can work that out. Because the slope, the derivative, is our velocity. So all we need to know is the slope of the tangent at that particular point of the graph, and that will tell us the instantaneous velocity at any particular time. We could carry that through. Now, a velocity graph now is just a fancy way of saying, hey, let's draw a graph of the derivative. And so we can do that. We know that stationary points, well, that's when the velocity must equal 0. Makes sense. If you're travelling and change direction, remember, going up positive, going down negative, so that turning point is when we change direction. It's impossible to change direction without stopping. Many have tried, stripped the gears in their gearbox, trying to do fancy things, trying to be clever, but it doesn't work. Even if you have to stop for like an instant, there is a point in there that you must stop, which a friend of mine also, and this one actually is true, not that the others I tell you aren't, but this one's actually true. A friend of mine tried to apply the laws of physics to a policeman. Because you know how at a stop sign you must come to a complete stop. So he's rolled up to the intersection and rolled back and then gone forward and off. And the police pulled him over because he didn't come to a complete stop. And he said, well, hang on, sir. I rolled forward, then rolled back. And he said, yes, that's right. Then at some point I must have come to a complete stop because it's physically impossible not to stop. And it didn't work, he still got a ticket. Okay. But, so we get stationary points. Nice name for when we're using these. The inflection point is when the second derivative would equal 0. So actually that's where the acceleration would be 0. But it turns out then, because acceleration is the first derivative of velocity, if it's the second derivative of displacement, then it's the first derivative of velocity, so we get a stationary point on the velocity graph. And if we wanted to find the instantaneous acceleration at that point, again, we could find the slope of the tangent. So let's now put in that acceleration graph. Other things we see, now whilst I don't know the equations, I can look at it and say, hey, that makes sense. Because that sort of up and down graph we tend to recognise as a cubic. Differentiate a cubic, you get a quadratic, which is represented by a parabola. Differentiate a parabola, you'll get a straight line, a linear function. So that's the sort of thing you see happening in those graphs. Okay, so if the question has said, what is our distance travelled? Well, the total distance is 7 metres. We've gone up to 2, down to -2, back up to 1. But our displacement is simply -1. Right, so we started at 0, I've moved 1 in the negative direction. My average speed over the whole journey would be 7, distance divided by time. Whereas my average velocity is displacement divided by time. Now, the lovely thing about that then is travel graphs are fantastic, and if we got them, we can use them. We don't actually need them because we can just use the theory of calculus to solve the problems. So displacement x, they've given us a formula. If we were to draw it, it would be a cubic. So we're travelling along a straight line, and it wants to know what's the acceleration. It's basically saying, find a formula for acceleration. We've got a formula for displacement. So differentiate it once, I'll get velocity. Differentiate again, I'll get acceleration. So there it is, 6t minus 42. Find when the particle is stationary. Okay. Stationary points occur when the derivative is equal to 0, or more logically, in this question, particle is stationary when velocity is 0. Velocity is 0, it must be stationary. However you want to think about it, but we're solving the first derivative is equal to 0. So it's stationary initially, and again after 14 seconds. And people, hang on a sec, if we're stationary initially, how on earth do we move? And that then comes down to the acceleration. There must have been some acceleration at the start to give you a push, and off you go. Another little particle moving on the x-axis conveniently. Starts at rest, so again we're stationary at the start, but we're not starting at the origin this time, we're going to start at x equals 7. Acceleration has been given to us, 2 plus 6t. Find the position when t is 3. So right, they've given me acceleration, but this time I've got to go back the other way. So velocity, 2t plus 3t squared plus a constant. Let's go and find that constant. When t equals 0, v equals 0. Turns out to be 0. So in this case I would have got lucky if I'd forgotten to find the constant. So v is 2t plus 3t squared. Integrate again to get displacements. In this case I wouldn't have got lucky, because when t equals 0, x is 7. Constant is 7. I have my equations. Once I have those three equations, displacement, velocity, acceleration, I should be able to solve any motion problem. So where is it? T equals 3, sub it in, 43. So we know we're 43. However you want to write the answer. I mean, some people just simply say when t equals 3, x is 43. Some people like to interpret the problem and say, oh, look, after 3 seconds, the particle's at x equals 43. I tend to go, well, 43 units to the right of the origin. It doesn't really matter, as long as you explain your answer. Now, because people tend to forget the constants, I tend to do it via a definite integral rather than an indefinite integral. So for acceleration, I would actually write it as dv dt rather than a. And then I would, what's called, separate the variables. Effectively, it looks like I'm just multiplying both sides by dt. And then I'm integrating both sides. And then the limits of my integration, I simply match up. Now the initial condition said when t equals 0, velocity is 0. So down the bottom, I said, all right, t is 0, velocity is 0. At the top of my integral, I said, oh, look, I'm trying to link time and velocity. So I'll just use the pronumerals t and v. And then I'll just integrate both sides and we should come up with a solution. Now 0 to v turns out just to be v. On the right hand side we get 2t plus 3t squared. You see we're getting the same equations over there, but it's sort of forcing me to find the constant by making it a definite integral, so I can't forget to go and find the constant. And then to go and find displacement, now velocity I'm going to write as dx to t. Again I'll separate the variables. Now this time it was when t equals 0, x was 7. It then wanted me to find what is the displacement when time equals 3. So notice with this one, I'm not actually going to bother coming up with an equation for displacement. I'm going to get the answer straight away, because the right hand side will give me a value. So x is going from 7 to x, the right hand side is going from 0 to 3, sub in, move the 7 across and we get the 43. So I tend to prefer working with definite integrals rather than indefinite integrals with these questions. Let's look at some actual HSC ones. Now, there's a two-knot one, I guess. I think so. Particle moves in a straight line, surprise, surprise. Displacement in meters is given by this wonderful formula, x equals t minus 2 on t plus 2. T is in seconds. First question, what's the displacement when t equals 0? So nice, easy gift question to start off with. Simply sub in t equals 0. Ah, there it is, -1. So initially we're 1 to the left, or -1, however you want to write your answer down. Show that x is equal to 1 minus 4 on t plus 2. Basically, remember this is a two-knot question. they're giving them a really big hint here that, hey, you can rewrite x equals t minus 2 on t plus 2, and by the way, this is how you rewrite it. Can you just show me that it is true? So it is a rather easy question, but as I say, it's a 2-to-1. So all right, 1 minus 4, t, if I make that all one fraction, oh look, I do get t minus 2 on t plus 2. It does work. So there, x equals 1 minus 4 on t plus 2. Now, hence find our expressions for velocity and acceleration. And I guess that was to make the calculus easier, because I think it's easier to differentiate x equals 1 minus 4 on t plus 2 rather than the t minus 2 on t plus 2. Because the t minus 2 on the t plus 2, I've got to fully use the quotient rule and what have you. Whereas here I can just use the reciprocal rule. Because if I differentiate 1, I get 0. I got a constant on the top, so I'll leave that constant there, and this is minus the derivative on the function squared. So minus 1 on t plus 2 squared. Okay, there's my velocity. Again, I've got a constant on top, so I could use the reciprocal rule again. 4 is the constant, minus the derivative, so minus, bring down the power 2, t plus 2. T plus 2 is going to cancel with the squared bottom there, and we get minus 8 on t plus 2 cubed. So we have our three main equations. Did they ask us to do anything? I hope so, otherwise that just would have been a waste of time. Is the particle ever at rest? Give reasons for your answer. Alright, well basically you look at the velocity equation and hopefully can come up with the conclusion, is it or isn't it ever at rest? We've got a fraction with a constant on top. So velocity is that, well that can never equal 0. It's just impossible for it to equal 0. Particle's never at rest. I wonder if they would have accepted an answer like that, because I've simply said no, it's not, it's never at rest because it's never at rest. Possibly I should have explained whenever you got a constant on top or something like that to explain well how I know that can never equal 0. What is the limiting velocity? So as t approaches infinity, poor little particle's never at rest, remember? So it's just going along and going along, oh, please let me stop. But it doesn't. So basically we're saying what's the limit of the velocity as t approaches infinity? Velocity was 4 on t plus 2 all squared. Well, the limit of that is 0. And basically we're talking about a hyperbola, aren't we, if we were to draw it. It'd come down. Of course you could do it via a graph if you wanted to. There's the graph of E equals 4 on t plus 2 all squared, and so again we can see it's going asymptotic to the x-axis, or t-axis I should say. So whichever way you do it, it's 0. Of course you could just keep subbing in really big numbers as well. You could just punch them into your calculator and see what's happening. Right, 2002 question. Particle moves in a straight line. Whew, lucky for us. In case you haven't picked up on it, as far as tune-it's concerned, everything moves in a straight line. That's pretty much it. That's what they deal with. So, particle moves in a straight line. At time t seconds, its distance x, oh, tricky, sine function. Sketch the graph. I suppose this was just a really clever way of getting a question where they could just get them to draw a trig graph, because essentially that's all this question's asking. Draw the trig graph, x equals sine 2t plus 3. So, alright, amplitude is 1, going to shift the whole thing up 3, period is pi, I'll mark my divisions every pi on 4. So there's my axis. We're going to wind around 3 because we're shifted up 3. It's a sine curve. Sine curve normally starts at the origin, but this one is shifted up 3, and then the sine curve would go up, down, up, down, up, down, up, down, up, down, and woo, there we go, draw it in. So there it is, x equals sine 2t plus 3. Using your graph, or otherwise, find the times when the particle is at rest. In other words, when is it stationary? So really, you could just read off the graph all of the tops and the bottoms of the graph, because they're all the stationary points. So reading off the graph, when velocity is 0, the stationary points, I'm not going to solve the equation, I'm going to simply read off the graph. So it happened at t equals pi and 4, and it did say when the particle times and the position. So it was x equals 4, at 3 pi and 4 it was at x equals 2, 5 pi and 4 it was back at x equals 4, 7 pi and 4 is back at x equals 2, and so on, and so on. It would keep going. And this is the fun bit where you get to use your brilliant ability of the English language. Describe the motion completely. Now, of course, I suppose you could write, oh, it was a lovely day. The particle just bobbing along. What did I put? Oh, I used some big words. Oscillates. There's a good. Oscillates a real good one for true graphers. Yeah. So the particle oscillates between x equals 2 and x equals 4 with a period of pi seconds. That's how I describe my one. Okay. So a lot of talk for just a few questions there, but we'll do those ones.